So the topic of this presentation is multi-connectivity for URLLC. Yes. Okay, so the agenda for this presentation is first I will talk a bit about the principles of multi-connectivity, what are the resources you can use, and what are the investment trade-offs you can do. Then I'll talk a bit about 3GPP systems, and then I will, through the presentation, I'll mention some different application examples where things are not limited to 3GPP systems and the, you would say, very constrained definition of URLLC in those systems, but look to more, yeah, you could say, relaxed understanding of URLLC. So I'll just mention briefly about throughput enhancement because it's the first use case of multi-connectivity. Then look into how we can use it for reliability and latency improvement, and looking at different reliability models. And then I will also present some work we have done on burst length analysis. And finally, just mention one related work on ultra-reliable UAV control. So the principle of multi-connectivity is basically that you exploit multiple paths between your user device and then the network, so that you get a better connection to the remote host in the other end of the network, because usually it's the first link, the wireless link, that's the weakest or most vulnerable. So the different ways we can achieve multi-connectivity is that we can use more frequency carriers or channels, like indicated here. So you have a multiple carriers to the same base station, and yeah, an example could be to use 900 and 1800 megahertz channels, and then you have some independence because they are affected differently, these channels. But of course, you still have the same geographical constraints and possible shadowing and so on. Then we can also consider using multiple base stations or wireless links, basically to other base stations. That could be LTE and 5G base stations in different locations. So then you really have some independence in the geography in this way. And then finally, we can go one step further back, you can say, and consider different interfaces or technologies. So coupling 5G or LTE with, for example, Wi-Fi, which is existing many places. So far, the multi-connectivity that is used in 3GPP is considering only multiple carriers or multiple base stations. But when you're adding these different, you can say types of resources, so the frequency carriers or base stations or interfaces, you somehow have to determine how you want to use it. So do you want to use it for gaining more throughput, or do you want to use it for gaining more reliability? And so you can send additional data if you use it for throughput, or you can use it for redundancy data if you value reliability higher. So in 3GPP systems, usually it's very black or white. You decide if you want to use it for one or the other. But if you are adding also coding techniques, then actually you can get a more fine-grained or gradual trade-off between throughput and reliability. So you can somehow get the best of both, depending on how much you need. Then a little note on latency. Often we see that when you improve reliability, then statistically you also improve the latency. So I'll get back to some examples of that later in the presentation. Maybe I can just say if you have any questions along the way, then please try to interrupt me, because I don't know if I can see if you raise your hand. I have my presentation in full screen mode.
I'll keep an eye on the chat,
Okay, great.
as well. So, but do please speak out. But I keep an eye.
Yes. So in 3GPP systems, when we talk about multi-connectivity, we have these two options that are outlined on this slide. So the first is dual connectivity, which basically means that you are using multiple base stations, as I before, or you can use what is called carrier aggregation, where you're using multiple frequency carriers. The dual connectivity has existed since release 12. And what you should take note of here is that the aggregation point is the packet data convergence protocol, which is one of the higher layers, meaning that that you actually have, in dual connectivity, you have two independently coded and modulated packets being transmitted from each base station to the UE. And so you don't have any physical layer combining possible, but of course you have two copies, so you have two chances to receive the packet. And this dual connectivity, it also supports that you mix LTE and new radio base stations. So as the new releases are coming out, these techniques are becoming more and more flexible. I think the latest thing is that you have some asynchronous transmissions now, so you don't even have to have so strong synchronization between the base stations. In carrier aggregation, this has existed since release 10. Sorry. And in this case, you have one base station that transmits on multiple carriers. And here you have aggregation going on in the MAC layer, meaning that you need a tighter integration of the radio protocol stack. So you need more synchronization, you can say. Yes, so these techniques were both originally introduced to achieve higher throughput, but recently they have now become also candidates for achieving higher reliability, because this has become an issue with the new 5G service types, especially URLLC. So, as I mentioned, it can be used for throughput enhancement, and I will quickly mention one example of this. So this is some work from colleagues in Aalborg some years ago, where dual connectivity is used in an LTE system, in the way that you have a macro base station and you have a small cell base station, and then a number of users, where the user that will then be served by this dual connectivity is the one that's actually on the edge here. And we can see why that's a good idea in the results. So basically, they have a study where they find out what is the gain you get in the throughput when you use dual connectivity, and this gain is shown down here as the difference in the SINR between the two cells. So what is the signal quality? And if we assume that we have, you could say, so the point in between where we have the biggest gain, 100% gain, basically we are doubling the throughput, is when the SINR is exactly the same between the two cells. And this also explains why it's not so beneficial to use dual connectivity for throughput gain if the user is not in this position, because if we have a bigger difference, suddenly the gains are becoming quite small. Of course, we can still gain 10, 20, or 30%, but we need to be within some margin before it pays off. Okay. So that was just very brief about throughput gain. Now I'll go on to talk about multi-connectivity for, in particular reliability, but also as a secondary effect, latency enhancement. So a similar scenario is shown here as the one we had before, but where we use dual connectivity and in particular what we call packet duplication for reliability boosting. So packet duplication is when we have dual connectivity, but we send a copy or 2 copies of every packet on individual individual base stations, so individual links. And this follows the structure I mentioned previously. So we have the splitting on the higher layer, and we have independent transmissions from the 2 base stations, meaning that ACNAC and HARQ is also independent. Basically, when the UE sees or is able to decode one received packet, then it actually doesn't care about the next one that comes. It can just discard that. And so this fact that you are only interested in the first arriving packet, this means that there is a small latency reduction from that, because you always get the minimum of the 2 transmitted packets. Now the reliability is quite easy to estimate with this simple model of what we call a parallel system. So we have the reliability of one interface, R1, and the reliability of the other interface. Then we take 1 minus each of them and multiply them, and then 1 minus that is the reliability of the full system. So if we are using a blur target of 1%, so that the packets are coded in a way through each of these protocol stacks, so that it's we aim for 1% block level error rate, then the total reliability of the multi-connectivity or dual connectivity becomes 4 nines. So 0.9999. And that looks quite good. Of course, we are not all the way to the 5 nines that we talk about in 5G for URLLC. But that can be achieved if we adjust the blur target. But I want to just say a little bit about this difference. So for one link, we have just 1% packet loss, basically. So 1 out of 100 packets is problematic. But actually what we do is we try to use twice the bandwidth just to correct that one mistake out of 100. And putting it this way actually shows how costly it is to use this multi-connectivity or dual connectivity with packet duplication. So it's not very efficient, and we'll get a bit back to that. So currently there are works that are trying to reduce this extra overhead, but it is a difficult thing. So I have to excuse my throat a little bit. I've been a bit under the weather the past day, so I have a slight irritation. I hope it's okay for you. Okay, so in this case, we just saw we have this quite high overconsumption or overhead. So what can we do? So some years ago, we did some work where we tried to look at other ways to use, in this case, it was multiple interfaces, but in principle, it can be used in different settings. So our baseline was this cloning or packet duplication case where you have the maximum reliability, but a very high bandwidth consumption. So you duplicate all the packets, and then you gain a little bit in latency because you are only interested in the first arriving copy. We extended this to look at what if we use some type of coding where we can actually split the payload. Instead of just duplicating, we can split it in a coded way in individual packets so that we just need to receive some amount of bytes, so slightly more than our original payload from different sources, and then we can actually decode the payload. And there are different coding techniques to achieve this. And the rationale behind this is that, one thing is bandwidth consumption, but another thing is that smaller fragments are also sometimes faster to send. So you don't need as long transmission time. And I've tried to then illustrate two examples, or the two specific examples we are looking at. So the first one we call K out of N. And here we use equally sized fragments. In the case of 2 out of 3, we basically we are sending approximately 50% of the byte, or you could say the size of the payload we send on each of the interfaces. Which means that we can transmit it faster. And then we just need to receive 2 out of these 3 fragments. And it doesn't matter which 2, just 2 of them. And so I've tried to illustrate over here, as soon as we have received the second one, then we are satisfied because now we can decode the payload. And then the last option is the most flexible one, where we use weights that are unique to each interface. So we have different sizes of the coded fragments. And then by designing these fragments, the size of these fragments, you could say as a function of the properties of each interface, we can actually optimize for reducing latency or improving reliability or reaching some specific level of reliability. I have some example results a bit later, but first I'll just briefly tell about how we approach this. So first, so the abstraction or the model we used is shown here on the right. So for each interface, we assumed that we have this blue curve, which is the latency that the probability that the latency is below some value x. So for some deadline of interest, that could be 1 millisecond if we're talking about 5G URLLC. Then we can check, okay, for this interface, what is the probability that that the experienced latency will be below this deadline or equal to this deadline? And then we go to out here, and then we can read off the reliability. And then obviously the outage that we can expect is then 1 minus the reliability. So we use this kind of description for the interfaces in this study. And for each point on the x-axis, you can actually compute then for the different strategies. So for cloning or packet duplication, or this K out of N, or the weighted splitting, we calculated the corresponding curves for when the interfaces are used in combination. And I have the results here. So these results are based on an assumption of each interface having 0.98 reliability. So not super good reliability, but we had some numbers that we got from a previous project from Telekom Slovenia. They have done some measurements on their networks. So what I would like to point out here is, we have different curves for each of these strategies. We have these K out of N strategies, and the one that is called 1 out of 4 here actually corresponds to the cloning or packet duplication. So every interface carries a full copy of the payload. And then the last one is the weighted splitting, where we have used a brute force algorithm to determine the best weights or the best way to distribute the payload across the interfaces. And what we can see here is that for some latency target, so we have considered some legacy systems here. So it's some old technologies, but anyway, we then set a target of a latency of 0.7 seconds and try to optimize for that. And we see the weighted optimized result here is actually the best reliability we can get of all the considered ones. And what is in particular interesting is when we compare it to the blue line, which is the cloning or the packet duplication, you can see that we actually have a decade of reliability improvement. So we have 1 more 9. Yes. What we can note here is also that of course, the cloning is the best reliability when we go to very high latencies or high deadlines, so at the rightmost part of the figure. So about these results, so they're quite distinct here, but you can unfortunately only expect that when you have legacy systems and you have quite large payloads. We also tried to do some measurements to verify our results. So we have this setup on our campus where we have GPS synchronized Raspberry Pis, and then we are able to send packets every 100 milliseconds between these devices, and then obtain timestamps and that are very accurate. And in that way, we can calculate what is the latency of the different technologies that we then tried out. And here we tried out LTE and HSPA, so a 3G technology, and Wi-Fi. So if we consider first what is the performance of single interfaces, and we look at 0.99 reliability, we have to go all the way down here. So it's between 50 and 100 millisecond latency. And that's quite high and not suitable for many low latency applications. But then if we apply these packet duplication principles, we can, first of all, we can achieve very high reliability. If we look at LTE plus HSPA, that's the purple one, the purple pluses. It climbs up here and it does not move very far to the right, actually, so we can achieve very high reliability. Or if we combine with the Wi-Fi, which we actually found was a bit surprising, we are able to exploit the the low latency of most Wi-Fi packets. Or maybe let me just explain the results of Wi-Fi first. So we see that Wi-Fi has a minimum latency of like 4 to 5 milliseconds, but it's only sustained with approximately 0.9 reliability. So in itself, if we look to the 0.99 reliability, Wi-Fi it quickly becomes worse than the cellular technologies. But when we combine them, we actually can benefit from this ability of Wi-Fi to push the cellular technologies to the left. So the best combination is actually these three technologies together, and we reach 5 nines already at 45 milliseconds approximately. Yeah, so even though Wi-Fi is terrible alone, it can really help to reduce latency. Use it with multiple interfaces.
So, Jimmy, where did you do the aggregation between the Wi-Fi and the LTE?
Yeah, well, actually, we have cheated a little bit because we measured these interfaces independently, and then we played back the measurements in a simulation to obtain these combined curves. So of course, if you have a system where you need this low latency, you have to make sure that it's handled in real time on your embedded device, let's say.
Okay, thanks.
Yeah. Now I will move to talk a little bit about what also is important for reliability, which is dependency on a common infrastructure. So when we talk about single connectivity or dual connectivity, or what we call interface diversity, then so single connectivity, we have basically a single point of failure from the UE all the way to the end host. In dual connectivity, we add another base station, so the wireless link that is usually the weakest becomes more reliable. But we only consider, usually it's only one operator, it's the same operator. So if we have some outage going on in the core network, then both connections will be equally affected. So this is where interface diversity has a potential advantage. You can actually use two operators core network independently. And then I have used again this parallel systems theory to or series and parallel systems theory just to characterize the reliability of these three solutions. And then we assumed some reliability values, based also on what we have seen in our measurements. And without going into too many details, so our core network we consider is quite reliable. So we have one case, the standard case is 3 nines, which is the upper curve over here. And then for the lower curve, we try with 4 nines reliability. And what we see is that the core network reliability actually is bounding the overall reliability for both single connectivity and dual connectivity. Whereas the interface diversity solutions, they can achieve a lower end-to-end outage probability, so higher reliability than the others. Yes. Yeah, and again we see that adding this unreliable technology Wi-Fi, even though it seems not so intuitive that it can do a lot of good, we see that it actually helps quite a bit when we look at the reliability. Yes. Now I would like to talk a bit about a different aspect of reliability than just you could say the original URLLC requirement. So in 5G that was defined as the probability that the latency of our data exceeds 1 millisecond, that probability has to be less than 10 to the power of -5. But this requirement, it actually does not say anything about the distribution of errors. So is it allowed that we have 10 consecutive errors and then 10 years of no errors? It's not really defined just in this requirement. So we actually wanted to look a bit into this, because we had this idea that some services may have different needs. So some services may be able to tolerate that we have like sporadic errors that are not consecutive, but losing a packet from time to time, if it's just a single packet, maybe not will maybe not cause any disruptions if it's, let's say, a control loop where you otherwise have some prediction going on. In other cases, we may be very sensitive to any interruptions, and in that case, we actually want to have long periods of uninterrupted traffic. So we actually set out to investigate how can we best use, let's say, LTE and Wi-Fi interfaces. And LTE could just as well be 5G, but we didn't have access to 5G interfaces, so therefore we looked at LTE. And the way we approached this, very shortly explained, is that we obtained measurements, basically the same measurements that I mentioned before, and we used those to parameterize a Gilbert-Elliott model that we then used in the further. And our results are shown here on the right side in the plots. So this complementary series shows, so each line shows what is the probability that an observed burst length exceeds this x value, so on the x-axis. And this, the top one shows the good burst, or the good state burst distribution. So for how long time are we in a good state where we have any interruptions? And in the comparison we did, we compared what here we call it UR, so ultra reliable LTE or ultra reliable Wi-Fi. So basically we looked at what if we have LTE with 4 nines reliability or Wi-Fi with 4 nines reliability versus using dual connectivity with LTE, so 2 times LTE or 2 times Wi-Fi, or combined LTE and Wi-Fi. And for the good state burst distribution, we actually see that LTE provides the superior results. It has much longer good bursts than any of the other solutions. The combination of LTE and Wi-Fi is also quite good, but it's still only half of the other one. And the other perspective is what is the length of the bad states. So when we have an error, how many consecutive errors do we see? And in this case, shorter is better. So in this case, we also find that it's actually not these ultra reliable LTE or Wi-Fi interfaces that are the best solutions. It's actually the 2 times Wi-Fi that is the best in keeping bursts short. And the next best is LTE plus Wi-Fi. Yes, so that was just a little bit about this study that we are currently extending to consider how can we best choose these different strategies, or some. No, let me rephrase that. So as we saw before, when we use these dual connectivity solutions, we have a lot of overhead and use extra bandwidth. So we are trying to see how we can avoid this extra bandwidth, so really reduce that by using some machine learning methods. Unfortunately, we have not finished the work yet, so I was not able to present it today. Okay, now an example of multi-connectivity in 5G. In 5G, we have what is called the new radio mini slots, where each mini slot is just 1/7 of the length of a normal slot, and this means that that you can actually put in the whole procedure of having a first transmission and then having HARQ feedback and then a retransmission within the latency budget of 1 millisecond. And in this work that is done by some of our colleagues from Aalborg, they tried out and compared single connectivity and this multi-connectivity. As you can see, the resource usage is double as expected, and in a scenario where we have the same link quality for the two interfaces or the two links, the single connectivity has a quite high outage, but the multi-connectivity actually manages to reach the 5 nines, but it also costs double the bandwidth. Now, if we instead compare what is the resource usage, if we let the interfaces have 10 to minus 5 outage, then we need to do a blur targets that are different, that are shown down here in the table below the plot. And we see, now it's the things are shown in a slightly different way. So we have the two scenarios here and different INR, but we have that basically still the same difference in resource consumption, meaning that single connectivity is the preferred way to obtain this URLLC requirement. But the thing is that in many cases, you don't have the link budget to actually achieve this blur target. So in those cases, you have to use the multi-connectivity. Then the question is, how do you know which cases? And that's a topic for future research. And then my last example of some work for dual connectivity is in relation to UAVs, and it's some measurements that were done here in Aalborg. So over the fjord, they sent a UAV to fly this path that's indicated on the map. And then there were some different networks available, and the drone was flying in 40-meter height, and then there were two modems with two public LTE networks, so different operators. Each interface was both sending packets of 1250 bytes, one per 100 milliseconds, and was also receiving the same. Let me just move this. So what we can see is that each of the interfaces actually perform not so good. So the outage is relatively high. It's 11.5% and 1.5%. But when we combine the two networks, so look at when were both of them in outage, we actually see that the outage is very low. If we convert it into nines, and it's very close to 4 nines reliability. Then I tried to just do a quick calculation of what I would expect, and I would not expect that good results. Actually, I would have expected this 0.173% outage when just assuming that the interfaces are independent or networks are independent. So when we get this much better result, it somehow has to mean that that there must be some negative correlation between the outages. So in other words, that when one network had errors, then the other one did not, and opposite. So that simultaneous errors were actually very rare. Yes, and that actually concludes my talk. So actually, I lost a bit track of time, so I hope you can tell me if if I was too long.
I think you're doing fine. I also lost track of time. I was paying attention to this because it's very interesting. We have a question. Stanley, please go ahead.
Yes. Hi, Jimmy.
Hi.
Thank you for your presentation. Regarding your presentation page 15. Page 15, you simulated multi-core network as a diversity redundancy. So here, do you simulated the core network as different layer? I mean, multi hubs, or do you just use a general model to cover the overall core network?
I just used this simple model shown here, so this reliability model. I did not simulate in different layers or so, no.
Okay, thank you. And this model is derived by the probability assumption from could you tell me more the background idea about how to model this this core network model?
Well, I simply consider the core network as just one component in the system. And then, yeah, when you go from dual connectivity to the interface diversity case, assuming you use two different operators, then you have that in as a part of the parallel connection here. So you have two parallel connections from the UE to the to the cloud or the internet here. So basically, in that case, you're not relying on a single core network to function. So of course, in the core network, you have redundancy and multipath and so on to achieve a high reliability inside an operator's core network. But experience has shown over the past years that even though the operators are doing everything to keep it reliable, then some small stupid mistakes can lead to the whole network crashing down in no time. We have seen some examples in Denmark where I think it was a switch configuration that was as a very seemingly innocent change in switch configuration that was rolled out to all switches at the network, then caused all kinds of havoc, and the network was down for several hours until some human operator was able to track it down and mitigate this error.
So here, in your right, the figures in the right, the RC in interface diversity part, the RC1 and the RC2. Here, what is the difference between RC1 and the RC2?
Well, it can be the same value, but it's just one for each operator. So if you have knowledge of, or let's say, if one of them is Wi-Fi connection, then of course you have a weaker Wi-Fi link, or the RL will probably be lower because the Wi-Fi is more unreliable. But then the RC, the core network, here it actually extends all the way to the Ethernet plug on the Wi-Fi router, or maybe even includes the Wi-Fi router as a component. So in that case, the RC would be lower than in the case of a 4G or LTE or 5G network, where the components are of higher quality.
Okay, so it will be like a fixed model, fixed random variable. Sorry. So in your simulation, the RC will be fixed in a fixed random variable in your simulation. So, for example, it will not be changed by time in your simulation.
No. Well, I did not actually do simulation. I didn't do time simulations over time. So for these models I have here, the equations, I tried varying some of the parameters and see the outcome. That's what I have plotted here.
Okay.
But yeah, it's a very high level perspective where you consider things as just black boxes, as components, and then you can study from that perspective what is the reliability of the system.
Okay, I got it. Okay.
Thank you. Any other questions?
Yes, one question regarding where you combine different links with each other. I think it was slide 12 or 13, when you add Wi-Fi to LTE, Wi-Fi to HSPA. Yes, here it's 13.
Or was it this one?
14, yeah, this one. It seems there is not much difference between when we are using LTE with Wi-Fi or HSPA with Wi-Fi. Is that so?
No. So I think these results, so the LTE, the model that we used for, the measurements for LTE here was done with a modem we had in our lab. So I'm not sure exactly which release of LTE it conforms to, but it's definitely not a recent one. So probably one of the first versions. And HSPA, I remember when LTE was first released, there were in some countries they actually had HSPA that they also branded as 4G because the speeds were similar and performance was similar to the first edition of LTE. So I think definitely if we had a more recent modem and did the measurements again, then we would see a bigger difference.
Okay. Thank you.
Welcome.
That is an issue with these systems, that the last releases of HSPA was definitely on par with the early LTE releases. I can understand that it's hard to see any big differences between those measurements. Good, thank you. I think that in interest of time, we will thank Jimmy for his interesting talk, and we will continue to the next speaker.